Hello everyone, this is a brief review of the Chapter 2 reading. Chapter 2 is our first introduction to using scientific data to draw a well-supported scientific conclusion. The research question here centers around something known as therapeutic touch. This is a therapy that is currently used around our nation, where a practitioner purportedly feels human energy fields emanating from someone's body without actually touching the body, and then using their hands removes negative energy from the body, thereby purportedly improving the patient's condition. This is a controversial therapy because there's not a lot of evidence that it actually works. One of the studies that challenges its effectiveness was done by Emily Rosa and her colleagues, as you read about in the reading. The figure on the right is a visual depiction of how the procedure might work. The person on the left is the practitioner. They are positioned behind a screen, so they cannot see Emily or where Emily's hands are. And they place their hands under the screen. There's little holes that they put their hands in, palms up on the table. And then Emily would flip a coin to determine which of the practitioner's hands Emily would place her hand over. And then the practitioner would have to decide, is Emily's hand over my right hand or my left hand? There would be 10 trials, so the practitioner would have 10 opportunities to decide whether Emily's hand was over their right or left hand. And so you would expect, if people are able to sense human energy fields, they would do quite well. They might get 8, 9, 10 right out of 10 tries. If, on the other hand, that they cannot sense human energy fields, you might expect them to get like maybe around 5 right on average, because they're doing 10 trials and there's a 50-50 chance, so they might guess right. You would expect them to guess right at least half the time. Sometimes when you're answering scientific questions with data, it's helpful to think about what supporting evidence would look like before you actually collect your data. So if these practitioners can sense human energy fields, you might expect some data that's highly skewed, like what you see up here in this top graph. Again, participants have a chance to be right 10 times. Of course, they have a chance to be wrong 10 times as well. And so they could, the number of possible correct answers they could get would be ranging from 0 to 10. And that's what these numbers are down here. The height of the bar, of course, indicates the frequency of that response. So if the participants were very good at sensing human energy fields, you would expect them to do well. And you'd expect them to, maybe the most common score would be 10 out of 10. But certainly you'd expect a negatively skewed distribution where most of the responses are 8, 9, 10. And then maybe there's a few who maybe had a bad day, who knows? However, if they cannot sense human energy fields, you might expect a curve that looks more like this one, where most of the answers are in the middle. This would be suggestive evidence that they can't really sense human energy fields. They're just guessing. Now, why are some people doing really well in this theoretical data set? Well, sometimes people get lucky. Maybe one person just through chance guessed 9 out of 10 times right. It'll happen sometimes. Notice some people didn't guess very well. So this is what you would expect. Something, kind of a normal curve based or centered around the middle of the correct response options, around 5. So now let's look at what the actual data looked like. You have 4 displays of the data over here on the right. A frequency bar graph, a stacked point plot, a box and whisker plot, and then a frequency table. Each of these different ways of displaying the data, this is the same data displayed in all 3 displays. Each of these ways has its own advantage, has its own something that makes it easier for you to identify important or useful data and draw a useful conclusion. This frequency bar graph shows you the general shape. It looks not normal, but it is, you can tell, centered around the middle of the scale. You'll notice that the number correct goes from 1 to 8 because no one got 9 or 10 correct. No one got 0 correct. So those options are displayed. It shows you that most of the scores are centered between 3 and 5. Remember, 5 is chance performance. There were a few people who did better than chance, but most people are doing below chance. Looking at the stacked data point plot, this is really the same information you saw over here, except turned on its side. You can see that if you look at a score of 1 over on this frequency bar graph, there was 1 person who got a score of 1. There was 1 person who got a score of 2. And that's why there's 1 data point across from 1 data point across from 2. There were 8 people who got 3 correct. That's why there's 8 points right across from 3. So really this information is the same. It's just displayed slightly differently. Going down to the box plot, the line that runs through the center of the box right here is the 50th percentile. That means 50% of the scores are at or below 4. Again, 5 is chance. The bottom of the box, that line there, is at 3. That means 25% of the scores are at or below 3. The top of the box is the 75th percentile. That means that 75% of the participants scored at or below 5. Again, 5 is chance. Not very compelling data. Then you have the frequency table, which has the advantage in that it is very precise. You can look at any score and determine what percentage of the people got that score and what percentage of people are at or below that score. So if you think of 5, again, 5, it tells you that 78.6% of the people scored at or below that score. Again, it's a little more precise than the estimate over here of 75%. Okay. In terms of scientific conclusion, this data does not seem to be very compelling in the sense that it does not suggest that the therapeutic touch practitioners can actually sense human energy fields. Now, you always want to be careful. You don't want to draw firm conclusions from just one single data set. But if you look at the literature on therapeutic touch, most of the studies that are done with good methodology show that the practitioners are not very good at even sensing human energy fields. For the remainder of the video, we're going to talk about central tendency and variability. These measures help you determine well, help you make scientific conclusions. We used central tendency in the previous therapeutic touch example because it helped us identify where the center was. What was the typical response of the therapeutic touch practitioners? Here's the data down here. Again, the center was somewhere around 3, 4, 5, right? Somewhere in the middle. Certainly not around 8, 9, 10, what we would expect if they were doing well, if they could actually sense human energy fields. Well, that's going to be the case with a lot of scientific questions. It's going to be helpful to be able to identify what the center of the data is and how spread out the data is. And as I alluded to in the previous chapter, the way you determine which measure of central tendency you should use comes down to the scale of measurement that the variable is measured on. If the variable is nominal, you're going to use the mode. If it's ordinal, you're going to use the median. If it's interval ratio, you're going to use the mean. You should also consider, when it comes to interval ratio data, whether the data is highly skewed or if there are outliers influencing the data set. While this distribution is not perfectly normal, it is certainly normal enough to use the mean. It would have to be very highly skewed in order to jump down to using the median, and you'd have to have an outlier. You'd have to have a data point way up here or way down here, far away from the other data points, to call that an outlier. Now, as I indicated, you have 3 different ways of representing center: the mode, the median, and the mean. And the way they define center is somewhat different. The mode defines center as the most common score. The median defines it as the middle score. And the mean defines it as the point that balances distances from the mean above and below the mean. Or, in other words, it balances deviation scores. And I'm going to explain that more in the next couple slides. But before I jump there, it is possible to have the mode, the median, and the mean give you the exact same score, even though they define the center separately. If you look at this symmetrical curve, you will see that it has the same mean, median, and mode. That will happen when you have perfectly symmetrical curves. But when the curve is skewed, you can see that the mean, the median, and the mode give you different values. The mean will always be pulled towards the longer tail, as will the median, but less so. Let's talk a little bit more about this defining center with the mode, the median, and the mean. Here I have a distribution of scores, just a list of scores right here. And the mode is, as we said, the most common score. So if you look through this list of scores, you can see 3 is the most common score. There's 2 of them. It's the only one that has more than 1 score. So that is the mode. The median is the middle score. This has 7 scores in this distribution. And so after they're arranged in order, the middle score has 3 above it and 3 below it. That makes 7 the median. 7 is also the mean in this case because, as you know, you add up all the scores, divide by the number of scores, and that will give you the mean. But I want to talk a little bit more about what that mean is doing, how that mean is balancing deviation scores. So what's a deviation score? Deviation score is the distance of a score from the mean of the distribution. So the mean of the distribution is 7. 3 is -4 away. This 3 is also -4 away. This 4 is -3 away. 7 is, of course, right on the mean, so it's 0 away. 9 is +2 away. 10 is +3, and 13 is +6. What I mean by balancing the deviation scores is that if you add up all the negative deviation scores, you're going to get negative 11. If you add up all of the positive deviation scores, you're going to get positive 11. This will always happen. That's what the mean does. It balances deviation scores. Now in this case, the median and the mean were the same. In other words, you had 3 negative deviation scores and 3 positive deviation scores. That does not always have to be the case at all. You could have just 1 or 2 negative deviation scores, and then all the others be positive deviation scores. You could do that, but in order for that to happen, this 1 or 2 negative deviation scores would have to have very high deviations, because the negative deviation scores and the positive deviation scores will always balance out, because that's what the mean does. An activity will point this out. Now we need to talk about the variability and the choices you have for measuring spread or the variability of data. You have the range and the standard deviation. The range is simply the distance between the minimum and the maximum score. So you would find the minimum score, find the maximum score, find the difference between them, and that's your range. The problem with the range is it's very insensitive. What I mean by that is it's only using 2 data points. Out of all of these data points, it's only using 2 of them. All of these numbers in the middle could change, and as long as they weren't changed to be more extreme than the minimum or the maximum, the range wouldn't change. So if you can change a bunch of numbers and the measure of variability doesn't change, that's a pretty poor measure, because it's not sensitive. It's not changing when the data changes. Standard deviation is a lot more sensitive. If you change even one number, the standard deviation will change. The standard deviation is the typical distance between all the scores and the mean. It will use deviation scores like the mean does. And what it's really you can kind of think of it as an average deviation score. It's not literally an average deviation score, but if you think about it that way, you'll be more right than wrong. Now I'm going to talk very briefly about how to compute the standard deviation using this formula, or this approach, which is a definitional approach. There's a computational approach as well. The definitional approach helps you understand what the standard deviation is. It defines the standard deviation better, in that it is more easy to understand. So let's walk through the computation, then we'll interpret what it means at the end. So the first step is to find the deviation score for every score. So again, we did this previously. 3 has a deviation score of -4, and so on. You just do that for all of them. Find each score's deviation from the mean of 7 in this case. The next thing you do is you square these deviation scores, which I did over here in this column. Then what you do is you sum all of these squared deviation scores, and you'll get 90. That is called the sum of the deviation scores, or the sum of squares. Be better to call this the sum of the squared deviation scores. That's what it is. It's the sum of the squared deviation scores. Now what you need to do is find the variance, and then finally the standard deviation. The way you find the variance is you divide the sum of squares by either n-1 or n, depending on whether this data comes from a sample or a population. Then after you turn it into a variance by dividing by n, or negative n, or n-1, you then take the square root of that, and that will give you the standard deviation. This is the standard deviation of a sample, and this is the standard deviation of a population. And what I mean by that is, if this data were a sample, this is what the standard deviation would be. If this data were a population, this is what the standard deviation would be. Now, let's just focus on the sample standard deviation for now. What is that saying? It's saying that the typical, or quote average deviation of scores from the mean is 3.8, 3.9 if you round up. If you look at it, you have some scores that are more than the standard deviation away, this one, and this one, and these others are less than the standard deviation away from the mean. It will always be like that. The standard deviation is the typical or average deviation of scores from the mean. Some are going to be more than the standard deviation away, and some are going to be less than the standard deviation away.